Our next video for today will be on covariance and correlation. So this is a way of thinking about kind of how linear is the relationship between a set of data points. So if you have data, right, that if you graph it and it looks something like this, there's a very clear linear relationship between this data, okay? Whereas if you have data that's kind of more randomly spread out, something like this, there's not really necessarily a linear relationship between these data points, okay? And so covariance and correlation are mathematical tools for measuring how much of a relationship there is between the data points as far as a linear relationship, okay? So the first of these is what's called covariance. So let me write down some notation. So as before, xi, yi are our data points. So x1, x1, y1, x2, y2, so on and so forth are our data points, right, from the data set that we want to model. X bar and y bar will be the mean of each data set. Okay, so for example, x bar is equal to x1 plus x2 all the way up to xn divided by n. It's the average value of all the x values. Similarly, y bar is the average value of all the y values. Okay? So if we have those, what we do is we take kind of the standard deviation between x and y. Okay, so it's a similar kind of calculation to what we had for standard deviation. So we define the covariance, which we write COV of xi, yi is equal to the sum from I equals 1 to n. So you add them all up. Xi minus x bar times yi minus y bar all over n minus 1. Okay, and so just like when we talked about standard deviation, there's this n minus 1 term down here where you might expect to take an average over the n terms. Don't worry about it. That's there for a reason. That's we'll talk about that in Math 313. Or if you haven't taken that class already. Okay? So the idea of covariance is that if xi and yi have a linear relationship, the absolute value of covariance will be large. Okay? So if you take this and calculate it, you'll get a large covariance if there's a linear relationship. If you get something close to 0, right? So if the absolute value is small, if it's close to 0, then that means that there's not really a linear relationship between the two. Okay? And so I'll show you, I'll do a calculation in Excel in this video that you can see kind of how this works and get the covariance. Okay? So let me just give you an example. So if you've got the points 1, 3.12, 2, 6.52, 3, 9.87, and 4, 11.37. The covariance of xy of these two data sets is going to be 4.6833. Okay? And that's in Excel. You'll see the Excel document attached to this. You can do the calculation there. It'll walk you through how to get it. It'll also show you how to do it. There's an Excel formula that gets this for you automatically. Okay? So that's covariance. Let's talk now about correlation. So the problem with covariance is that you can have two very similar data sets, similar in some important sense, similarly linear, with very different covariances. So for example here, 1, 3.12, 2, 6.52, 3, 9.87, 4, 11.37. These are, we get a fairly large covariance. There's a nice linear relationship between these 4 points. And if you graph them, you would see that right away. Okay? But if you take these each and multiply them by 100, so 100, 312, 200, 652, 300, 9.87, 400, 1137. The linear relationship between these is just the same as the linear relationship between these, right? If you graph the points, everything's just been scaled up by 100. They're not necessarily any more linear than each other, but the covariance has increased by a factor of 10,000. So the covariance here is 46,833. Much, much larger, even though this set is just as linear as this set. Okay? So this is a problem. Covariance depends on scale. And so the question of what does it mean for the covariance to be large depends on what data points you started with, right? So is this a large covariance for these data points? It's kind of tough to tell. Okay? And so what we do is we introduce something called correlation. Okay? So the correlation, which is denoted generally by R. So R is the covariance of xy, so this number we just found, divided by S sub x times S sub y, where S sub x and S sub y are the standard deviations. So if you remember the standard deviation of a set of numbers, which we computed earlier. So you can take the standard deviation of all the x values times the standard deviation of all the y values, and you'll get this correlation. Okay? So now with this correlation, if we take this through and we divide out, what happens with each of these, so even though here the covariance is 4.6833, here it's 46,833. When we divide through by the standard deviations, which are also, here the standard deviation is much larger than the standard deviation here, it normalizes things out. And in this case, we get R equals 0.98677. And here we get R equals 0.98677. The correlation doesn't depend on scale, okay? It just depends on what the linear relationship is. And here we have a very linear relationship, okay? So you can see again the calculation of this in the Excel spreadsheet. It goes through all of the details to get the correlation for both of these data sets. And I just want to talk a little bit about how we look at correlation. So R is between -1 and 1, always. So the R value will always be between -1 and 1. There's theory behind that. Don't worry about it if you don't want to know it. You can learn it in 313. It's always between -1 and 1. R equals -1 means negative correlation when x goes up, y goes down. R equals 1 means positive correlation. which is to say when x goes up, y goes up. And r equals 0 means no correlation. Okay, so r equals 0 means that they're perfectly random, that they're totally randomly organized. There's no linear pattern at all. Now, of course, in practice, the numbers end up being somewhere in between. So we got 0.9867 for our previous example, 9868, something like that, which means we're very close to 1, which means we have a very strong positive correlation. Okay? We'll talk, again, in Math 313, we kind of go through all the details of how large does it need to be. But in this class, we're just going to think of it as being, if it's close to 1, it's a strong positive correlation. If it's close to -1, it's a strong negative correlation. If it's around 0, there's really no correlation. Okay? The other thing you should be aware of is that programs like Excel a lot of times will use R squared. So R squared gives you a number between 0 and 1. If it's close to 0, that means no correlation. If it's close to 1, that means there is some correlation, whether it's positive or negative. And so it works the same way. If you've got an R squared that's very close to 1, it means you've got some correlation. And then you can tell whether it's positive or negative by whether the line goes up or down. So Excel uses that. R squared, we'll talk about this when we talk about the regression line. R squared gives you the percentage of the value that is kind of determined by the regression line. Okay? And that's the piece that a lot of people are interested in.